The story is about a generalization of what's called symmetry-protected topological phases and a related concept, the de Hooft quantum anomaly, to what's called average symmetries. So let me start by quickly remind you what are these words in the usual setting. So symmetry-protected topological phase is really a natural generalization of the topological insulators to strongly interacting systems, right? So specifically, we're talking about a Hamiltonian system that's gapped with a unique ground state. And in the ground state, if you measure correlation functions, it's all short range correlated. They all decay exponentially. So at least within the bulk, the state looks almost boring, except when some of the symmetries, let me call it protecting symmetry, is preserved. The state is non-trivial in the sense that it cannot be adiabatically connected to an atomic insulator or a unentangled product state. And if you break the symmetry, the state looks really boring, really trivial, because it can be adiabatically connected to the trivial state, to the product state. So famous examples include the free fermion topological insulator and the Haldane AKLT spin 1 chain. One thing that's famous about this type of state is that on the boundary, the thing looks more interesting, right? So the well-known examples include the topological insulator, where if you go to the boundary, the state no longer remains insulating. It has gapless fermions that are protected, right? If you want to gap out the fermions, you need to do something drastic, break the symmetry or something. Likewise, for the Haldane chain, we know that if you go to the end of the chain, there is a dangling spin half moment that you cannot cancel out because you just have a bunch of spin ones in the bulk. So of course, for a given bulk, you can always have multiple types of boundaries depending on your boundary condition, depending on what Hamiltonian you put on the boundary. But there is something that's universal, that's robust. That is the quantum anomaly. Right? The anomaly, which is provided really by the bulk, tells you that your boundary state cannot be trivial in the IR. In fact, it has to be non-trivial in some specific way. Right? Here, by non-trivial, I mean, for example, it cannot be gapped while simultaneously preserving the symmetry and without having any topological order, right? So it's something that guarantees non-trivial IR dynamics at the boundary. Okay. By the way, if you have any questions or anything, just feel free to interrupt me anytime, any point. And of course, the notion of quantum anomaly, the de Hooft anomaly, exists not only on the boundary. The boundary of an SPT is kind of the most natural place where it arises, at least for within the context of quantum many-body systems. Of course, in quantum field theory, people have been playing around with this kind of thing for a long time. And still within the realm of quantum many-body physics, actually there is a place where a quantum anomaly arises quite naturally. That's in systems where you have Lipschitz-Matisse type of constraints. Okay, so let me be concrete. The specific example you can think of are spin systems. Let's say you consider a spin system, a lattice of spin systems, where you have lattice translation symmetry, and within each unit cell, you have some spin half moments, or more generally, some half integer spin. Okay? Let's say you have spin rotation symmetry, SO3. Right? And it turns out if you have this symmetry with this Hilbert space structure, whatever low energy state you get, you will get a specific type of de Hooft anomaly. In fact, it's a mixed anomaly between the spin rotation symmetry and the lattice translation symmetry. So that will prevent you from having a trivial ground state. Right? So we know that. In fact, Lipschitz-Matisse proved this, even before the word anomaly became a thing, quite amazingly, that for this type of system, the ground state has to be either spontaneously symmetry breaking or gapless, or later people figure out that in dimension higher than 2, higher or equal to 2, you can have intrinsic topological orders, right? If you have a gap and it's symmetric, it has to have, you will have inevitably any excitations, right? So these are pretty powerful constraints on the IR dynamics. And there are many generalizations. It doesn't have to be SO3, it can be Z2 cross Z2, it can be time reversal. Also, the lattice symmetry doesn't have to be just translation, rotation, reflection will also work depending on details. So it's a powerful thing. For this talk today, the question I want to ask is how exact are the symmetries have to be for all those stories to hold? And in particular, I want to ask, I want to think about a situation where I have some quenched disorder. I mean, I always have in reality. And those disorders, for each realization of those disorders, some of the symmetries are broken, actually. Right? But if you average over all the disorder realizations, the symmetry is restored. Right? The most familiar example are, in fact, lattice symmetries in any realistic crystals. In any crystal, I always have some dirt, some impurities, some lattice defect. So when we say that the system has translation or rotation symmetry, at best, we mean that those symmetries are there upon disorder averaging. Right? So the question is, if some of the symmetries are only true as an average symmetry, does the notion of SPT still make sense? Does an anomaly make sense? Right? And if they do, what do they mean? What are the consequences? So that's the type of question I want to ask. So here's the plan of the actual talk. It roughly consists of 3 parts. So the first part is I want to be a little bit detailed. So where I want to define what I mean by average SPT. Right? So here I want to be detailed because I want to make it clear what is my rule of game. What am I really playing around with? And then after defining the notion, I'll try to give you some physical pictures and construct some non-trivial examples, give some understanding of this. So that will be the second part, and then I'll go to the boundary of this average SPTs and talk about the consequence of average anomaly. So for the second and third part, my goal is to give you an overview of what's really going on. So I won't, my arguments will not be as detailed. The details are in our paper. If you're interested. Okay, let's start. So let me first remind you how we define the usual SPT in the conventional setting. So we think about a local Hilbert space, this one, and then we consider gapped local Hamiltonians, right? And then there is a symmetry, SPT, the S refers to symmetry. So I have a symmetry that commutes with the Hamiltonian. Right? Standard story. The non-trivial thing here is that I demand that this local Hamiltonian has a unique ground state that's gapped. And as a consequence, this state, further, I demand that this state is short-range entangled. In the following sense, that there is an adiabatic path. So there is a adiabatic evolution that takes you from this ground state to a completely trivial state. Right? Here, completely trivial state, if you're thinking about a spin system, it could mean that all spins pointing up. Right? More precisely, or more generally, I want this trivial state has no entanglement. It's a unentangled direct product state. Okay. Or if you think about fermions, then think about an atomic insulator. And the fact that, so when we say that this psi is a non-trivial SPT, it means that this adiabatic path exists, but the Hamiltonian along this adiabatic path must necessarily break my symmetry G. Right? So if I preserve my symmetry, then there is no such adiabatic path. The state is distinct from the trivial state. It's true, for example, for topological insulators, for Haldane chain, and many other non-trivial examples. The standard story. So now let's think about disorder ensembles, right? So you see that this slide is a little bit dense. It has many items, but most of these items you find are pretty physically intuitive. Nothing really too non-trivial here. So let's go through it one by one. So I want an ensemble of local Hamiltonians. Each one I want it to be gapped. So that Hamiltonian, you can think of it, it can be a little bit more general, but it doesn't hurt to think of it as a clean part plus a disordered part. So this VI, so little I is the lattice site index. So V, think of it as a random field that couples to some operator, right? So this operator, local operator O, I demanded to at this point the only demand is that it's local. It has involves non-trivial operators only around the site I. Okay. And I want so this V has some probability distribution over some domain. The only thing I demand here is that V's are short range correlated. It doesn't hurt to make it like, completely uncorrelated in space, which is usually what people do, but having an exponentially decaying correlation function doesn't hurt. Okay? By the way, the bar here just means averaging over the disorder ensemble. Now let me define the symmetries. So there are two notions of symmetries here. So one notion is called exact symmetry, which is more similar to the symmetry in the previous slide. So let me call it K. So an exact symmetry would commute with the Hamiltonian for any disorder realization. So it doesn't matter what value this V takes in ensemble, the K will commute with the total Hamiltonian. Okay? That's the exact symmetry. And then there's the average symmetry, which is the main player of today's story. So this symmetry, let me call it G. And the non-trivial thing here is that under G, this O, this operator O, transfers non-trivially, transforms non-trivially, right? For example, if G is some Z2 symmetry, then this O is some Ising spin. Right? That's odd under this Z2 symmetry. And equivalently, that you can say that this means this random field V is also transforms non-trivially under G. Okay, but the fact that we call it an average symmetry is saying that the probability distribution of V is symmetric, is invariant under G, right? Even though individual V is. And for this talk, let me focus on the simplest case where the total symmetry of my ensemble is just the direct product of these two. Right? So it's exact symmetry, direct product with the average symmetry. In general, it can be much more complicated. In general, it can be a non-trivial group extension. But let me just focus on the simplest case. So then, analogous to what we call to the symmetric states, which are eigenstates of symmetries, but in the clean case, here we want to talk about a symmetric ensemble, meaning this total symmetry G is not spontaneously broken in the ensemble. So that's the kind of thing we want to play around. And let me and now I'm ready to define the notion more seriously. So we need some analog of the short range entanglement condition. Right? Remember, for the clean case, we want our ground state to be at least when the symmetry is broken, to be adiabatically connected to the trivial state. Right. So what's the analog of that for our disordered ensemble? Well, one condition that's immediately intuitive is that I want the state psi I for the ground state psi I for each disorder realization. Let me label each disorder realization as capital I. For basically whatever value this random field V takes, I want the ground state to be short range entangled in the sense that that ground state is gapped with exponentially decaying correlation function, adiabatically connected to the product state. Right? So that's intuitive, I think. Then there's the slightly less intuitive, but if you really think about it, it makes sense physically, is that I want any two different realizations in my disorder ensemble to be also adiabatically connected to each other. This, in fact, doesn't follow from condition number one, so basically psi I and psi j for two different disorder realization I and j, they should be adiabatically connected. And I demand that the adiabatic path should also preserve the exact symmetry K. This is to forbid things like, for example, like you can think about an ensemble where you have some states with let's say if you think about the 2D electrons, right? 2D electron gas. If you think about an ensemble where half of your states has Hall conductance +1 and the other half has Hall conductance -1, that doesn't count, right? That will violate this condition, right? Let's say if you have U1 symmetry preserved, for example, right? But if you if you start from a clean insulator and add quenched disorder to break some symmetry, to make some symmetry average, then as long as you don't hit a phase transition, then this condition will be preserved. By the way, let me emphasize that although I'm putting in this condition, I'm not assuming that the disorder is weak in any sense. I mean, the disorder can be pretty strong, but I want to maintain this adiabaticity. Okay, so and then I'm finally ready to really define my gain. So analogous to adiabatic evolution of my Hamiltonian, I can define continuous deformation of my system. I can continuously deform the clean part. I can deform the operator that couples to the random field. I can also deform the probability distribution of my random field. But I do want to preserve all the previous conditions I mentioned while deforming this. So I don't want to cross any phase transition while deforming my system. In particular, I want to keep all the symmetries. The exact symmetries should remain exact. The average symmetry should remain average. The system doesn't spontaneously break any of this in middle, and the system remains short-range entangled throughout. Okay. So that's the continuous deformation. That's the class of deformation I want to think about. And now it's kind of obvious what to do next. Then I just define average SPT as basically equivalence classes under such deformation. so that's the rule of my game. And so before I go to actually construct some non-trivial examples and some further understanding, is there a question about the first part? All right, so then let me continue. Before going to the detail, let me give you the basic idea, the rough picture of why how to characterize a non-trivial SPT phases with average symmetries, right? So remember with the standard SPT, let's say topological insulator, one way to think about it is through the topological response, right? And very roughly, this is not completely accurate, but it works in most of the cases. The topological response is characterized by the fact that symmetry flux traps symmetry charge, right? So probably the most well-known example is the integer quantum Hall effect, where if I have a U1 flux, if I have a unit quantized 2 pi U1 flux, there is an integer U1 charge trapped by the flux, right? That integer is labeling your Hall conductance, right? So flux traps charge. That's that basically characterizes 90% of the SPTs we know. Now if we think about average symmetry, what you can realize is that, well, charge is not well defined, right? Because for each individual realization of the Hamiltonian, the symmetry, your ground state may not even be an eigenstate of the average symmetry. So charge is really hard to define. But flux can be well defined. There is no difficulty there. So for example, if I think about a Z2 symmetry, an Ising symmetry, and I make it an average symmetry, right? So what is a Z2 flux? Well, a Z2 flux basically means in some direction, let's say you have a periodic boundary condition in space, then in some direction, I make the boundary condition anti-periodic by this Z2, right? So if I have some field phi that's odd under the Z2 symmetry, a flux means that, sorry, is there a question?
No, I don't think so. I think.
Okay, great. So so to make this to make an anti-periodic boundary condition, I just make the condition that phi at x equal to L, L is your system size, to be minus of phi at x equal to 0. Okay, that's usually how we do it. Right? You can do that for Ising. The only thing you have to do in addition to that, in the context of average symmetry, is to also flip your random field. You slightly modify your disorder ensemble, right? Just like how you slightly modify your Hamiltonian, you insert a flux in the usual setting, and that's it, right? You look at you make that condition, and then you recalculate all your properties again. Right? So it's a totally well-defined thing. And once you have that in mind, it kind of becomes obvious what to do, right? So if the usual SPT means flux traps charge, well, then an average SPT can be characterized basically as saying average flux traps, well, you cannot trap average charge, that doesn't make sense, but exact charge makes sense. So you can certainly have something that has the property that average flux traps exact charge. Right? So that's the basic idea. So now let me go to the a more detailed and concrete construction. So the idea of flux trapping non-trivial objects, you can formulate that in terms of response theory to a probe gauge field and so on. That's a well-defined formulation. From a field theory point of view, that's probably more natural. But let me give you approach it from an angle that's hopefully physically more transparent. So let's think about what's called the decorated domain wall construction. So let me first tell you how it works in the standard case, in the clean SPT. So the idea is you start from a state that spontaneously break the symmetry G. And then you can have domain wall excitations in that spontaneous symmetry breaking phase. Just to be concrete, let's think about a Z2. You have a Z2 symmetry and it's spontaneously broken. So it's like an Eisen ferromagnet, and then you can have domain walls between spin up and spin down. Right. But the non-trivial thing is on this domain wall, I decorate, essentially I put a lower dimensional non-trivial SPT state, or in general some topological state, and then I can essentially condense this decorated domain wall in the sense that I form superposition of such domain wall configurations with arbitrarily large domain wall. So if this domain wall isn't decorated with anything, this is a well-known procedure to produce a paramagnetic phase, right? To produce an Ising paramagnet. But if this domain wall is decorated with stuff, then you get something non-trivial. Let me give you a concrete example. Let's think about an SO3 cross Z2 symmetry, right? The O3, if you like. But what I want to do is on this Z2 domain wall, I put an SO3 holding, and I proliferate the domain wall to form this gigantic quantum superposition, right? Just like what this picture is showing. Each of this blue loop is a domain wall, right? This plus minus sign is the pattern of the Z2 symmetry breaking. So once they form coherent superposition, I restore my Z2 symmetry. In this massive superposition, my Z2 symmetry is no longer broken. This is a state that's symmetric under both SO3 and Z2. Turns out if you choose the superposition coefficient appropriately, the state is short-range entangled. It has exponential decaying correlation functions and so on. And this is known to be a non-trivial SPT protected jointly by SO3 and Z2. So that's the standard construction. Now let's think about the average symmetry SPT case. Well, the picture is actually very similar. You can certainly start again from a state that explicitly break the Z2 symmetry. Let's again think about SO3 cross Z2. And let's think about Z2 as an average symmetry now. So we start from the symmetry breaking state, and then we can have domain walls. And then we can have states decorated on the domain walls. So in this case, let's decorate an SO3 Haldane chain, a non-trivial Haldane chain to the domain wall. So the picture is very similar, except here we don't condense the domain walls. We don't form quantum superpositions of the domain walls. Instead, the domain walls don't really move. Domain walls look classical now because where the domain walls appear essentially are decided by the realization of my random field of my quench disorder. Right? If I have my random field pointing upward, pointing up in this outer region and pointing down in the lower region, then my domain wall is basically in between, okay? And it doesn't really fluctuate. However, the domain walls do proliferate, not in the quantum sense, not as a quantum superposition, but at the level of classical probability. Right? In this disorder ensemble, I'll have this configuration where I have domain wall like this, but then I'll have a different configuration with domain wall structure like this, and then yet another configuration with domain wall like this. So as long as my Z2 symmetry is not spontaneously broken, in this ensemble, I will have configurations with arbitrarily large domain walls. This means that the statement that domain walls are, I'm sorry, I should also say that this domain wall proliferation at the classical probability level is also what restores the Z2 symmetry in my ensemble. Right. So once I have restored the Z2 average symmetry, well, I still have the SO3 exact symmetry. Then I can ask on the domain walls, what's being decorated? If the answer is that it's a non-trivial Haldane chain, well, that's going to be clearly different from having nothing decorated on the Z2 domain walls, on the large Z2 domain walls. In fact, you can argue more carefully that these two cases are really distinct. So this construction actually gives you a non-trivial example of average SPT protected jointly by the SO3 exact symmetry and the Z2 average symmetry. So the picture does look very, as I said, does look very similar to the clean case, but it's not completely the same. There is one crucial difference, which is in the average SPT case, the domain walls, as I said, they proliferate probabilistically, not as a quantum superposition, which means there is no analog of the superposition phase factor. Remember, here in the fully quantum case, in the clean case, when the domain walls proliferate, I do have a choice of the phase factor in the superposition here. For example, here I can choose plus or minus sign, but as an average SPT, that choice has no meaning. Right? There is no such a thing as the superposition phase factor, and as a consequence, the SPTs that are non-trivial solely because of that phase factor becomes trivial once the symmetry becomes only an average symmetry. So let me give you an example. It's actually just the example just now, which is if I have a Z2 symmetry in 2 dimension, in 2+1 dimension, there is one non-trivial SPT known as the Levengood state. And the picture is the wave function, the prototypical wave function is extremely simple. It's basically a superposition of all the domain wall configurations, except with a non-trivial sign factor. Basically, you get a minus sign if you have odd number of domain walls. Right? If you have even number of domain walls, you get a plus sign. So this is, it turns out, this is distinct from the wave function with just +1 throughout, and it's a non-trivial example of SPT. So it turns out if I make the Z2 symmetry on an average symmetry, this state has no analog. It basically becomes a trivial state. So more generally, I can think about the K cross G symmetry, the exact cross average symmetry, and within the so-called group cohomology classification of the bosonic SPT, the boson SPTs are classified. If I generalize the argument I just outlined in the previous 2 slides, the classification is this object. Okay. And compared to the clean case, right, for the clean case for the G cross H, there's a similar expression in terms of the Kuhn formula. If you compare with that, then this expression is just missing one term. It's this term, this H to the comma H to the upper D plus 1 with G, the average symmetry with the U1 coefficient. So the meaning of this term is that it's a group cohomology SPT protected solely by the symmetry G. Right. So so the conclusion is that within the group cohomology formulation, states protected solely by the average symmetry becomes trivial. Right. If you want to remain non-trivial, it has to be at least protected jointly by an average and a exact. That's true within group cohomology. If you go beyond group cohomology, it turns out there are examples that's not like that. But let me just not go there, just for simplicity. So that's what I want to talk about for the bulk. Right? So the example is to give you some example. Sorry, the goal is to give you some example, to give you an overall picture of how this works without going into too much detail. Right? And before I talk about the boundary dynamics, the anomaly, and so on, is there any question about that part?
There is a question, actually.
Yeah, go ahead.
I have a very naive question regarding the SO3 exact symmetry and the disorder realizations. So you're saying that one is preserved in all the instances?
Yeah.
Can you just maybe recall what the SO3 is here?
Think about it. You have some SO3 spins, right?
So 1/2, and
well, it doesn't have to be spin 1/2. It can be spin 1. Yeah.
Okay. Do you want? Can it be spin 1/2 or?
You can.
Okay, let's spin 1. Spin 1 is fine.
Yeah. Yeah.
Then you have a domain where they're all polarized down in the middle, and they're
no. The spins don't transform under the Z2. If you want to construct some solvable model, the easier thing is to to have 2 separate sets of degree freedom. There's the spin. There's another icing spin that transforms only under the Z2 and not the SO3.
I see.
And then you can let the icing spins. You turn on some random field for the icing spin. Don't touch the SO3 spin, but the icing spins do couple to the SO3 spin in some non-trivial way that preserves the SO3 symmetry. Roughly think of this icing spin as some random bond provision to the SO3 spin system.
So in this picture, you're just showing the Z2 variable, and the SO3, this other degree of freedom is not shown in this.
Right. It's not shown. The only place where SO3 is relevant is on this blue circle I have. Okay. So now let's talk about anomaly. Since this is a CFT conference, I feel anomaly may be more fitting to the theme, since we know anomaly has been extremely useful for the study of CFT. So you can ask now, if I go to the boundary of this SPT, we know that for standard SPT, anomaly gives me very strong constraints on the boundary dynamics. Right? It's essentially saying that the boundary, if the boundary does not break the symmetry spontaneously and is not doesn't have some topological order or something, then it basically has to be gapless. Right? Very often it's a CFT. So what about the disorder case? Right? What about the average symmetry? Does the average symmetry anomaly have similar power? So let's look. Well, the answer is basically yes, but so again, let's use this previous SO3 cross Z2 average SPT as an example, right? So before everything I was talking about the bulk, it was the system was put on a space without boundary. Right? But now let's put the system on a space with boundary, okay? And re-examine this boundary, and then the question is, does the anomaly? If it's in the clean case, the anomaly will tell me that once I have a boundary, this system cannot possibly be short-range entangled. At least on the boundary, I'll end up with some long-range correlation. Then you say, what about this case? So now let's look. Let's suppose, right, that for some disorder realization, this the system, even with the boundary, is short-range entangled, right? So with only exponentially decaying correlation function with a finite correlation like C, and it has a clear gap. And suppose that happens for some disorder realization, and let's see what happens. Well, that alone actually doesn't give you any contradiction. Turns out, it seems fine. But what you can do now is that since the state, as by assumption, doesn't spontaneously break the Z2 symmetry, we can always create a domain wall with arbitrarily large size by going to a slightly different disorder realization. And that disorder realization is also very simple. Just flip all the random fields within this region A. This region, I call it A. So that way I create a domain wall at the boundary of this region A. Right. This is what we pretty much the same thing as what we did in the previous two slides. The only difference here is that my boundary now touches the physical edge. Right. So this domain wall has the boundary. However, we already said that this domain wall, what's living on this domain wall is a Hordane chain. So when the domain wall has a boundary, the Hordane chain ends up having a boundary, having two boundaries, right, two endpoints. But the Hordane chain is famously known to have dangling spin 1/2 moments at the boundary, at the end. So what we end up having by flipping the random fields within this domain A is two dangling spin 1/2 at the end, at the two ends on the physical edge. Well, by assumption, the original state is short-range entangled. So meaning if I change the local Hamiltonian, the change only affects a finite region nearby, right? So that means that regions far away from this domain wall, right, let's say on the boundary, this part, or regions deep inside this part, they don't see the domain wall. So they just do what they originally were doing anyway, right? Short-range correlated and all that. So they couldn't couple to this dangling spin 1/2. So they couldn't absorb the spin 1/2 moments. We do want to get a ground state that's SO3 symmetric. So the only way to make the state SO3 symmetric is to lock these two dangling spin 1/2 into a singlet. Right? Essentially, you don't have any other degree of freedom to play with. I already said this region A is arbitrarily large. That means by just flipping the random fields in this region, which in terms of the probability of this realization is the same as before, because I have this average Z2 symmetry, right? So this random fields has same probability of going up and going down. So it doesn't decrease my probability of realization. So without decreasing realization probability, I've created a singlet that's arbitrarily long ranged. And there are infinitely many ways to do such things. I can create another domain wall here, another one here, and if I'm in the thermodynamic limit, there are infinitely many such ways, all with essentially the same probability as the original, as the disorder realization of my original state, which was assumed to be short-range entangled. Which then means that that state I started, which was short-range entangled, at best has a vanishing probability to be realized in the thermodynamic limit, right? So realizing that particular state doesn't really violate anything, unlike in the clean case. It's fine. But the statement is that in the thermodynamic limit, the probability of having such a realization must go to 0. So the conclusion is that if I do have this type of boundary anomaly, if I have a non-trivial bulk average SPT, the boundary with probability 1 in the thermodynamic limit has to be long-range entangled with arbitrarily long range, at least with arbitrarily long-range singlets, right? Maybe there's no realization at all with short-range entanglements, not even just with vanishing probability. That will also be consistent with this argument, right? But the conclusion is that even if you manage to find a realization that's short-range entangled, that realization must have a probability that dies that goes to 0. So that's the statement. So the statement is average symmetry, average anomaly does provide very non-trivial constraints on the IR dynamics, similar to the clean to the standard anomaly. So one application, which there are some steps of arguments which I'm omitting just for time's sake, is that you can apply very similar arguments, and within a few steps, you reach the conclusion. You reach a similar conclusion, but for lattice system, not on the boundary, just a lattice system on its own, but with LSM, Lipschitz-Matisse type of constraints. So specifically, you can have the following statement, which is if I have let's say a lattice spin system with exact spin rotation symmetry, SO3. In fact, it doesn't have to be SO3. You can have Z2 cross Z2 subgroup. You can have time reversal, as long as it's an on-site symmetry that admits some projective representation. It's okay, right? And then you have some projective representation per unit cell. Let's say spin half for the case of SO3, or Kramer's doublet for the case of time reversal. And then you have the average translation symmetry, right? So it's think about a random bond, a Heisenberg model or something, right? Then it turns out this type of system will also have an average anomaly between the exact on-site symmetry and the average translation symmetry, with very similar consequence. And in fact, the particular case with SO3 on-site symmetry and one-dimensional chain was proved in an earlier paper by Itama Kimchi, Adam Nahum, and Sento. So this ours is like a generalization of that statement. It doesn't have to be, in fact, it doesn't have to be translation. You can do rotation, reflection. There are many different versions of this kind. And in fact, the picture I showed you when arguing for the consequence of the anomaly is very similar to the story of random singlet state in random bond antiferromagnetic spin 1/2 chain. So the random singlet state turns out is a classic example that satisfy this type of anomaly constraint. All right, so I think time-wise I'm doing fine. So here's the summary of what I've told you so far. So the main message is SPT and to hope the anomaly makes sense, even for exact symmetries, right? Even for average symmetries, and many of the things we talked about for in the clean settings do make sense. Right? Things like topological response, decoration of domain walls, and the long-range entanglement guaranteed by the de Hooft anomaly and LSM, right? So these things turn out they all make sense and have with non-trivial consequence. So let me end by mentioning some of the open directions that we can explore. So there are many. I only mentioned very few things. There are many more things that one can explore, probably should. So we can generalize the problem to SPT of mixed state. In fact, this has been done recently. It has been discussed recently in the context of open quantum systems. But with in disordered systems, it makes equal sense. We can also ask about whether there exists intrinsically disordered average SPT, meaning it's an SPT of some average and exact symmetry, but there's no clean limit. You cannot make a clean SPT with that same symmetry with the same response. This is some ongoing work that we're thinking about actively now. And you can generalize the problem with, once we talk about SPT, you can ask what about SET, meaning symmetry enriched topological orders, things like Théorie codes or Laughlin states and so on. What about the effect of average symmetry there, right? The other thing which might be more relevant for the audience in this workshop is that we know that historically, we know that anomaly provides extremely powerful insights into the dynamics of gapless systems, like things like CFT. Right? So then it's natural to ask: does the average anomaly provide equal amount of insight for disordered critical systems? Right? Things like quantum Hall plateau transitions, disordered spin liquids, disordered deconfined critical point, Y or Dirac semi-metals, and these are not completely academic questions either. Questions too, right? Because any real system do have plenty of disorders. So it's a question that one should think about, even just pragmatically. You can ask crazier questions. What about compressible state? Can we think about dirty non-Fermi liquids from this angle? What about non-equilibrium stuff? Right? Things like random circuits and so on. So with that, let me just end here. And yeah, thank you for your attention.
Thank you very much for this interesting talk. Are there any questions?
Thanks, Chong. I have a question about the example you mentioned in your slide before the conclusion, the spin chain.
Sorry.
So it's a Wendy spin 1/2 chain, Heisenberg coupling between nearest neighbors, and you're considering a distribution of random J's, right?
Yeah.
And so you're saying something is special about this. I just don't know about this. So maybe can you tell us a bit more about?
Yeah. If you look at the particular model where you only have nearest neighbor J's and J has some randomness, this has been solved in the 90s by Daniel Fisher, probably earlier, using methods developed earlier by Dasgupta and Ma. That's the random RG. So it's basically been solved. And the picture is they end up getting is for each disorder realization, it's more or less a bunch of static, meaning non-fluctuating singlets, but the singlets can range very far, can have very far separating, basically arbitrarily far separating spins locked into the singlet. So if you measure average correlation functions and so on, it's powerful. So of course that's for that particular model, nearest neighbor antiferromagnetic coupling. You can ask if I turn on crazier coupling, like quantic, whatever you like, right? It may not be as solvable as before, And then you can ask, can you get some state that looks less interesting, right? Some state that looks really with exponential decaying correlation function with any operator, no matter how you average it. The answer is no, right? And that requires something like what I said.
So you're saying that there's some anomaly that prevent, but this is not an average SPT, right? Because I mean, this
this
is critical or has on average power law.
If you like, this is mimicking the boundary of an average SPT. So it's critical system with average anomaly.
And the statement is that if you add other types of disorder, not just nearest neighbor Heisenberg,
the state still has to be somehow non-trivial. Right? So for example, that would not be true for spin one chain. Right? For spin one chain, you can start from the gapped state and add a little bit of bond disorder. Nothing will happen. It's still pretty boring, at least inside the bulk. But for a half integer spin, the statement is you can never do that as long as you keep the average translation symmetry. The SO3 or SU2 has to be exact. If you make that average, it turns out it's pretty easy to make boring state. Just polarize the spin. That's it.
Exactly.
Yeah. And that has to do with this thing I talked about. If all your symmetry is only average, the SPT-ness is gone. The anomaly is gone, and there's no constraint on dynamics.
And maybe I can ask a question about this slide because you're here and I wanted to ask, so it's a good, I'm lucky. Instead of looking at disorder average, so ensemble of density matrices, can you take that state, Levin-Goose state, and just remove the phase factors, or think about doing that for another SPT, which is an analog, quote unquote, of an ensemble average, but now you just have a pure state, but you've sort of killed the phases. Could that mimic an ensemble?
That's
of killing the phases, but you still keep superposition.
That would be an Ising paramagnet. That would be just a rewriting of all the x sigma x pointing in one direction, right? Or the sigma x.
What if you decorate the main walls with some non-trivial lower dimensional SPT?
Yeah.
Always get
this thing I was talking about, right? So if you so here I was talking about decorating the domain walls with Haldane chains, which in any case gives you something non-trivial. But when you superpose the domain walls, you still have a choice of the sign. If you choose the plus sign, so then it turns out it's just domain walls with Haldane chain. That's it. But if you choose the minus sign, it's actually that plus a Levin-Goose state. So it's still a non-trivial SPT, but it's in different class. It's a different phase. In fact, this SO3 cross Z2 is classified by Z2 square. Well, actually, there's another Z, but that's not important. But it's Z2 square. It's essentially this, whether you have the Haldane chain here and whether you have the minus sign in the superposition.
Can I actually ask a more kind of philosophical question? Since you said, well, basically, some of the kind of a non-average SPT normal ones, I just don't have the equivalence average, like this examples with the plus or minus with the slide afterwards, right, that you were showing now. So somehow it looks like some are not relevant when you start averaging over disorder. So do you say then that, I mean, in the real world there is disorder, right? So do you say then that the clean SPT actually are just not the things to study? They are not relevant to the real world. You've got
no. In real world, there's always disorder, but the disorder doesn't always break the symmetry, right? I mean, if I have an insulator, well, there might be some dirt in my crystal, but those disorders don't break the U1. So the U1 is still a pretty good average exact symmetry.
So I guess question is, if I keep disorder very low, but just a little bit of very, very low, I mean, is the clean case still relevant? And is there
sorry, that's your question. Yeah, I mean, if it's low enough, you can always neglect it.
So how low? What is
depending on your real resolution, right? If you're you know, in the real world, there's always disorder, but in the real world, you're never at zero temperature anyway, right?
Yeah.
So it all depends on your resolution. If your resolution is already below that disorder scale, then you shouldn't neglect that. I mean, it's the same reason why we say for topological insulator we require time reversal. But if you really think about it, time reversal is broken in the standard model.
Of course, yeah, it's always broken.
But we don't care about that. We never get to that resolution. So fine.
Okay.
Same thing.
All right, thank you. So thanks again for the talk.
Thank you.